I'm gonna be honest. These sections were not fun to self-study.
Okay.
And with hindsight, I'm like, this was not hard.
Uh,
But to actually figure it out without any help was like, okay. It took a second. There's lots of retrospective um things going on here. Okay. So if because now we're officially into the algebraic stuff. So it's no longer just open close. F prime are continuous maps of the O of the space into the space Y. We say that F is homotopic to F prime if there is a continuous map F that takes x cross I to Y such that f of x0 is equal to f of x, and then at the other endpoint, f of x1 is f prime of x, and that's true for all of the points x. And then here, the convention we're using is I is that unit interval, closed unit interval.
okay.
So the map, because it doesn't matter which closed interval you take.
Okay.
Um, so the map
That's interesting.
F is called a homotopy. It's called a homotopy between F and F prime. So if F is homotopic to F prime, we write, of course, we use this relation all the time. And then if F is homotopic to F prime and F prime itself is a constant map, then we say that F is null homotopic. We'll talk more about that when we actually get into like fundamental group and stuff. Today we don't really do much of this.
Not heard that one before.
Uh, so this is, yeah, we're doing deformations, the weird stuff. I thinking about that because whenever I look up topology articles, there's always kind of like the pop sci clickbaity, shapes kind of being
Right.
squished and all that. This is actually kind of that. I didn't know that though until I got to the very end of the section, and then I put kind of the pieces together at that point. Okay, definition. So if f taking this into x is a continuous map, such that f of 0 is equal to some x naught, and the other endpoint give me some x1, then we say that f is a path in x, I should say it's path in x1, from x naught to x1. We also say that x naught is the initial point, and x1 is the final point of the path f. And then of course, for convenience, um, we use I equals 0, 1 as the domain for all paths. Domain for all paths. Okay. So then we'll do path homotopic. So that's the more interesting one. Okay, so two paths, two paths will have f and f prime that take I to x are path homotopic. Path homotopic if they have the same initial point x and then of course final and the same final point x1 final point x1 and if there exists some continuous map, a continuous map f which takes I cross I to x such that there's two properties here that we'll illustrate. So if I have f of s and then 0, I want that to basically be the first curve or the first path. And then the other endpoint, f of s for 1, should be the other path. And then with respect to the so if I start at 0, no matter where I'm at for all of the different definitions, I should stay anchored at the initial point. And if I'm at 1, no matter where I'm at in the definitions, I should stay anchored at the final function. So those are our properties. And then these need to be true. I should specify for all s and t. And so we call a path homotopy. Between f and f prime. And if f is path homotopic to f prime, we write f. The construction of these definitions was very similar to when we did isomorphism with groups, because you talk about what isomorphic means, and then the definition of isomorphic means it needs a specific map, so let's call this specific map the isomorphism. So we have this specific map f, and we're calling that map the homotopy. So here's kind of I made a figure for this to help me understand what's going on. So if I take like that unit box, so this is 0, this is 1, this is 1 for s and for t. What's going on in here is like, so if I take that baseline, if I travel across here when I haven't done anything, that's the first, so this is f. And then as I travel along up here, that's where I'm supposed to end up when I'm performing to. And in the middle, there's a bunch of other stuff as I go across. So if I have like, maybe at 1/3, I have some sort of path that goes here, and then maybe I have another one. So this is 1/3, 2/3. And so what the path homotopy is doing is in the actual space X, this is X, then if I have some initial point, X naught, and then some final point, X1, then I can have some sort of a path that goes between those 2 points, and this is our F of S, which is the same as, we could think about it in terms of the big F, the path homotopy, as being S when our parameter is at 0, so the initial. And then we can think about where we end up as some F prime, this other path, which is now at the end, so FS1, because we're using 0 to 1. And then in between those, so it's like this path 1/3 could be something, it could be whatever it might look like. Maybe. And that is now F of S for this case when we're 1/3 of the way through our deformation. And maybe we'll get closer to that. Starting to deform it. So it's kind of interesting.
Right.
And we have hardware to do this kind of stuff.
So if you have the space X has a hole in it, I mean,
Right.
right,
You could have issues.
right, because you can't. Yeah, somehow you got that piece of string continuously, and if you encounter a hole, you can.
And it'll get
can't-
stuck.
Right.
Yeah. I think the homologies will do. I don't know if we'll get into homologies this semester or next. That's just because I haven't looked too far ahead. Although I did create a schedule for all the sections I'm gonna do to the end of the semester. And it's basically gonna be, I'm gonna finish chapter 9 and 10. And because that seems like a decent course, because then I'll have done chapters 3, 4, 5, 9, and 10. And that'll leave the really tough stuff for next fall. Okay. Okay, oh yeah, these relations are equivalence relations. So we should state that the relations homotopy and path homotopy are equivalence relations. And then I'll just leave a notational note for later and future times, is that if F is a path, we shall denote it's a path homotopy equivalence relate. So path homotopy equivalence class by, and you should have the algebra students come to some.
Yeah,
They'd actually start to get some of this more than the other. So we can just prove this real quick. Goes pretty nicely because stuff that's true about this almost immediately, like I think it's reflexivity and symmetry are pretty much the same. So given F, it is trivial. Always a risky word. That F is path homotopic to itself, because you can just use the map where you assign everything to just the path. This is the required homotopy. And then if F is itself a path, because technically we don't require F actually to be a path at first, but if F is a path, F is also a path. Oops, big F would become a half homotopy from the same exact homotopy. And so we want to show, of course, a good review of equivalence relations here, that f being homotopic to f prime implies that f prime is homotopic to f. And this goes, we later define this as the inverse element for the groupoid. But we can let f be, oh, I need to define the homotopy for it first. Let f be a homotopy between f and f prime. And now we can say if f, well, I need to subtract 1 from the variable, so then I have g xt. I'll define this map to just take this homotopy and reverse the order. And then this is a homotopy between f prime and f. So if f is a path, or I should say f, the big F is a half homotopy. If f is a path homotopy, that does not change the fact we can still construct that. So then G, so G. And then transitivity, want to show f homotopic to f prime and f prime homotopic to f prime prime would give that f is homotopic to f prime prime. Let f be a homotopy between the first two, so f and f prime, and f prime be a homotopy between the next two, f prime, f prime prime. Then we can define, again, a convenient map G that'll take x cross I, y by the equations, or it's really just an equation, g x t, and we'll split it. So we'll start with f x to 2t for t going halfway across, and then we'll use as the second part 2t, but we need to reverse it so that we can go from 1/2 to 1 and still preserve the fact that we're using I to x with the homotopies. Then the map G is well defined. Since the issue would be the connecting point t equals 1/2.
Make sure it's set.
We have that f of x 2t would be the same thing, which is how we define it to be f prime. And f prime is how we defined it to be f prime x 2t minus 1. And then we just kind of look, well, that would become 1, which is the end point, which would give you the next path. But then here that comes to 0, which means it's the initial point of the previous homotopy, which is the same thing.
Yeah.
And then because G is continuous, on the two closed subsets. Two closed subsets x equal and well x cross the first piece and then the second piece 1/2 to 1 of the overall x cross I. It is continuous. Well, this is pasting. I'll start pasting them in here on all x and I, or whoops, by the pasting lemma. So SG is the required homotopy.
Thank you. Thank you.
Homotopy between f and f prime prime. And if f and f prime are path homotopies themselves, then so is G, because we can observe two things. G 0t, so at the initial point, is the same thing as f0 to t, which is x naught. And if I do g1 of t, then that's the f prime 1 2t minus 1, which is the final point x1. So what's going on with this idea for the strategy is I'm going to start here with a unit box. So this is S, this is T, again, 0, 1, and 1. And to illustrate this, I'm going to split this into different pieces. So we're cutting it essentially at the half mark, right across the deformation here. And then, so we're going to have this lower part and upper part. So I'll maybe do this as a quarter. So 1/4, this is 1/2, and then this is 3/4. And so this bottom half will be treated under the first homotopy f that'll get us from 0 to 1/2 and then f prime from 1/2 point. And so if I take this and see what this gives me down here, I'm looking at this, which is 0 to 1, but then only 0 to 1/2 on t. And then just kind of, now that's the middle path going in between there. And then this also is being split into, when this one is the shaded one, stay consistent here. This is 1/2, so it says S is 0, but we have 1/2 in t. S still goes all the way out to 1, and t now goes up to 1. And then we'll take this in the middle. Whoops, that's 3/4. And then now, when we view it this way, when we come back to our space x, we have f, the path homotopy, and f prime as path homotopy. Stick it. So here is x naught. Here is our ending point. And that first path, again, just kind of something like have a path. This is our f of x, which is just the initial t. Somewhere in the middle, we're going to have a path that's kind of halfway through. So this is our f prime of x, which is halfway through. F of x 1/2. And then we're ultimately trying to get to some final f prime prime, which is f prime x. What? I almost forgot to switch it to right. And then in the middle, we're gonna first to deform to f prime using the first path homotopy. Oops. And then we will use the second path homotopy to deform up to the second. So then this will be what's happening in F. And then that happens on the second. Okay, so transitivity of deformation. Fine. Trying to fit these pictures in my little papers. Always fun. This is just a fun one for the application for the people who like, analysis and such. So if I take f and g as maps into R2, then I can define the homotopy f xt to be 1 minus our parameter times rf, and then fade out, fade in.
Yeah.
And then this we call the straight line. Well, it's not, this isn't the general form, but this is a straight line homotopy.
Like what, straight lines and linear? That's interesting.
Yeah. Between f and g. Because it moves each point f of x to the point g of x along the straight line. Segment joining them. Now if they're paths, then it's path homotopic. So there's two cases. So you don't actually have to have paths, and I haven't drawn one of those yet. So you could have a situation. Here's R cross R. And you could have your first map be something like that. And then you could have another map that you're going to be something up here. So they're not necessarily required to be anchored to the same initial point and final point. And so what's happening is that the straight line path homotopy is taking points f of x onto points g of x using line segments. So this would be f, this would be g. and any specific given f of x is given to some g of x. And then if we do actually have path homotopy, then it'll look similar to what we've been doing, is I've then start by anchoring down where I want to begin and where I want to end. And so if I have the map F and the map G, and then I'm taking F and deforming it this way. So then specific point of X in a straight line to the point G of X. And then this is happening for all different things. Okay. So now let's talk about products so that we can head toward the algebra stuff. If F is a path in X from X0 to X1, and G is a path in X from X1 now to X2, we define product, another one, another product, F star G of F and G to be the path H that is given by the equations. So I'll take my H. So what's frustrating is that it feels very intuitive, but then like expressing it is a little hard. The more intuitive it is to express, a little more difficult to describe. So since I can only go now, so before we were taking the deformation parameter and cutting that in half and then doing two separate deformations.
Right.
But now we're saying, okay, I gotta take a map, and my path is going to go halfway to an intermediate like stopping point to get ultimately to a new final point x2. So I have to think of fg as a path, and then f prime g prime as the path that I'm going to be going to. So I split x now in half instead of t. So I need to speed up the s by double, and then that lets me go from 0 to 1/2 for the s portion, and then for the g, I can do the same reverse idea as we did before, where I started the other end and then come back for the s's. Nice. And then h is well defined and continuous by the pasting lemma. And it is a path in X from X1 for for X0 to X2. I clear space for the picture. Yeah, I'll do that. Well, make it fit. Okay, so here I've got my good old box again. So this is 0 to 1 for S, 0 to 1 for T. And then now, instead of splitting it along here, I'm going to split it along S. So that we're going to go halfway. But we still have paths that are running through S. So we'll still have some path running through S. And of course there's more, it's just convenience. So we'll have G be the shaded stuff and the F 0 to blank. This is going to give us we'll start at 0, we'll end at 1/2 for S. We're still going all the way up to 1 on T. And this is still passing through it from 1/3. This is still passing through it from 2/3. And down here, this is now 0 for T, but 1/2 for S, up to 1 to S, and 1 for T. And we still have this crossing through it. This is the shaded. Okay, so under F, this is where we're gonna have our path homotopy, and then another path homotopy. Then here's a space. We'll start somewhere. And there's going to be an intermediate point in the middle. And then we'll end somewhere. Here we're going to go from X naught through the path F first. To here. And then G helps us finish. So it goes this direction. And then what we're eventually deforming to is some other path. Yeah, prime and G prime, respectively. Now these threads are still running through all the way. So the 1/3 mark is still going to be just going through as it does, and then the 2/3 mark would make it closer on the other side. So, I mean, the construction's pretty much the same. You're just going to it. The only reason why I draft this product to not like additive, but I think I know why they don't consider it additive, because this is not abelian. And so you don't want to suggest, especially if you're going to be doing algebra with it, that you've got something that is commutative. So, but this will be associative, but not commutative. So that's probably why, if they thought about their terminology, they went with that. Okay, write down this theorem because we will need to use it here.
Interesting. They didn't stick an extra word in there, like path product or something.
Yeah. I think it's a contextual product, as are all the products in this math, so. Because technically, to represent the input to the homotopy itself is a product, if you're thinking about point products in Cartesian product. Okay, so here's important. This will be important for the algebraic structure. So the operation star defined by. I actually had a flashback to my research when they were talking about this, because I did something very similar. And so that was relieving, honestly. Has the following properties. So we won't have a group here. We'll have a group one because of the right and left identities. One, we have associativity, of course. So if F star G star H is defined, which is important, then so is F star G star H. And these are the equivalence classes, not
Right.
which is interesting. Because then I was thinking about the difference between like if I take a loop or like a figure eight versus just a straight line. So I think they get into that more when we start looking at the fundamental groups. And they're equal. Are equal. And then our right and left identity. What's really interesting doing this right after grading all of their binary operation homework. So given X, and also part of it is that the textbook when I took that class didn't really have satisfying examples of the left and right identity. So this is nice. Let E sub X denote the constant path where we have E to sub X takes I to X, carrying all of I just onto the initials. Or not the initial point, to the point X as subscripted, then we'll start using the initial point. So if F is a path in X from X not to X1, then we have that if I take my path, if I go through the whole path and then map everything in the endpoint onto itself, then that returns to me just the path. And then if I started now by first mapping everything, the I onto X naught, and now I'm here at X naught, and then I just go through my path. It's the same thing as just going through the path. And then last, we've got the inverses, which we've already constructed essentially. So given the path F in X from some X naught to X1, we will let F bar be the path denoted by, and then just reverse it. So 1 minus F. Well, I should say F of S is equal to F of S is equal to F of 1 minus S. And it is called the reverse of F. Then, now that we have this, we have the inverse property from is that if I go down my path and then undo my steps, I should end up on the initial point, which is if I were to map everything onto the left, or the beginning of my path. And if I actually started at the final point and went back to the initial point and then retraced my steps through the path, I'm now doing the same thing as if I've mapped the entire interval I onto the endpoint. Right. So then there is groupoid. And just one more little theorem note here. I thought about proving this, but the proving associativity is very not trivial. There's some other constructions you have to do in the middle. I was like, that's a little bit a lot. If we had 2 hours, we would do that. So this is more just, we'll use this later for bigger results. Let f be a path in X, and let a not
I'm swinging back towards the HPE solution for the base solution,
Okay.
because they did include 5 years to 6 day service. And within that, year 2000,
Okay.
and so that's substantial.
It is. Right. Okay.
So I'm gonna be.
Are we still including the one piece?
Yeah, so I
Okay.
asked HPE for if they wanna be an all HPE solution.
If they can fix that.
To
then.
quote that
That's a good idea.
in row. And I'm getting another quote from Seth for just that component. And I'd like to toss in a bone. But I won't buy a cabinet from him because I want all the actual cabinets on.
Yeah.
I'm not.
Can HPE do the door stuff? Or
I'll
could we help?
get Seth to do that.
Yeah. Right. Cool.
I'll give him the profile of what it looks like and we'll go there. I think I'll still plan on going with tall racks. HP is continuing to give me 42 and 48 too. But I think I'll still go with the tall racks unless we find a reason that we can't. But pretty quick, I'll have probably tomorrow I'll have Bonnie go figure out. Or
Okay, cool. Thanks.
It's almost like steps.
Yeah.
Because now I'm thinking, well, that's a little bit different.
Because we did have that problem with the overlapping of the point, but this would fix it already.
Now that depends on how I want to then interpret what I really mean by
The octave.
that. Because this is suggesting now that we're operating on a path, which means you'd have to philosophically argue whether the frequency of sound should be viewed as a path. And I don't think I want to draw that conclusion. I know it was more just like math echoes itself. It echoes itself. So to see constructions like this is kind of like, well, I can understand the motivation for this kind of stuff. What I think I'm gonna do is after I review what I've already written and kind of just make that kind of a neutralize its claims a little bit, make it more palatable to the music community. That's really what it is. Because to math people, it's fine. I've now sent it to enough people who have PhDs that they would have told me something is like wrong with it
Sure.
if there was something wrong with it. So now it's just I need to tone down some of the music side controversies. Because then I think it's fine. I actually think it's fine at that point. So then the fall, I can work towards basically to follow that paper. Because I'm really not satisfied with where it is right now. Because
Okay.
it bothers me to know that I didn't really have a choice given my time constraints, but I'd like to not have to assume lots of the topological properties that I just assume from the get-go. And that's not like a bad thing because they're all very intuitive properties, but
It's okay.
yeah.
It's probably good to do it in stages because the current literature isn't even at your first stage.